We were just looking at unsupervised learning versus supervised learning, distinguishing this particular dichotomy of machine learning problems. And I'd like to tell you about some variations on these themes that people often refer to. So variations on these. So the first one is what's called semi-supervised learning, which is very interesting, sort of in between supervised and unsupervised. So in semi-supervised, you get, as in supervised, you get some sequence, some data, x1 through x, let's say, k. And then you also get just some more x's. So you get like xk plus 1 up through xn. And you don't get the y's for this last set of data points. And the task is, so given this, choose. So you could either say choose a function like we did for supervised, but typically people say, impute or predict the labels for these remaining points, y, n, for the unlabeled. So you call these the labeled points, and these are the unlabeled points. So this is typically how people set up the semi-supervised problem. But more generally, you could think about just I have a bunch of x's, and I have a bunch of data points, and so I have all these x's, and some of the values, some of the coordinates are missing. In this case, I distinguished y as a particular coordinate, but so that would be something sort of like the Netflix problem would be sort of like that. You have all these people, and some of the values like how well do they like movie X, or a particular movie, and you have to guess how well they would like that movie. Another area which people often talk about is called active learning. Oh, and let me just give you a little example of semi-supervised. So say I've got some data in R2. Oh, I should use our convention of superscripts. Stick with that. So these are 1 k plus 1 up to n, k plus 1 up to n. So if our points are, in this example, in R2, maybe we get some points like this, and they don't have labels. This is a classic sort of toy problem they call the 2 moons data. And then you get a label here, x, and a label here, which I'll denote by a circle. So this is from one class and this is from another class. And you have to figure out what are the labels of all the other points. So in this case, k would be 2. And typically you would say, well, this looks like it's from this red circle class, and these all should be from the green X class. So that's semi-supervised. Active learning is where you get, so it's something sort of similar here. What you're given is basically the same as this, and now you get to also you get to ask for the labels, the y's, for particular points. So first, maybe you're just given this, and you do the best you can, but then you get to ask for, so you get to say, tell me, so maybe if you want to verify this, so this point here, right, it's closer to the x, and you would like to know what the value of this particular point is. So you can ask in active learning, tell me the value of that point. And you get that label, and then you proceed to make your predictions, and maybe you get to ask for so you ask for this one, and then you get some more information. You ask for maybe this one, you get some more information. Maybe you ask for this one, and after you get to ask, you get the labels of a few more points, then you have to make your predictions. So that's active learning. And what else do we want to talk about? Let's talk about, so decision theory it doesn't really fall into these categories, but I think it's good to talk about it in this context. So in decision theory, so in all these, we were sort of assuming that you wanted to do the best you could on all these unlabeled points, on any other points that you have to predict, and we didn't really talk about how are we going to measure your performance on those other points. So one way that you might measure the performance is, something like how many you got wrong. So if there was, if you had to make predictions on capital N points, then you might say, the number wrong divided by N to measure your error. But you might take something else instead. And so, for example, in decision theory, so here's an example, would be if say you're a medical doctor, and this is sort of a classic example. If you're a medical doctor and you get patients, and you have to decide whether they have cancer or not, and you can so they either have cancer or they don't, and you can prescribe you can ask for a test or no test, like a biopsy. So they come to your office and you examine them, and so that's not cancer. So this is the true thing. They either have cancer or they don't, and you're going to either order a test or you're not. So if they, and so so there's a certain it's not just that you want to be, this would probably not be a good loss function, is what they usually call it, not be a good way to measure your performance on your patients, because, for example, if they have cancer and you do not do the test, then that's very bad. Whereas if they do have cancer and you do the test, okay, well, that's not not great. They have cancer, but you do the test and you can catch it. If they don't have cancer and you do the test, well, that's kind of bad, because they have to go through the test and all that. And if they don't have cancer and you don't do the test, well, then that's not too bad. So you might put values in here to describe a loss matrix. Like this would be maybe a large negative value, a little negative value, maybe these are 0. And so it matters, how you make your errors. And this loss matrix that they would call it makes a difference in what you choose to do here. So this would be like the Y's. The Y would be, do you test or do you not test? So this would be like the Y that you choose, and this would be something like a true. So the true Y would be like 1 here and 0 here, something like this. And the X's in this case would be like all of their symptoms, everything that you get to observe about them. So that's decision theory. And let me mention one more interesting area, which is a very sort of general setup called reinforcement learning. And in reinforcement learning, it's sort of like a sequential decision theory in some sense. Well, actually, that means something else. But reinforcement learning is, you have, say, you're think about it in terms of just your life. You're going through life and you want to maximize your overall reward and minimize your overall loss. And so associated with each, at any given point in time, you take an action and you get some reward or loss for that action. So there's rewards, losses associated with actions, and states. The state is what's going on right now. But it's not just sufficient to, you don't just want to maximize your short-term reward, like, well, I'm going to eat a bunch of chocolate and because I really like chocolate, because a few hours later, then I'm going to be sick to my stomach. And more, or longer term, maybe you think, well, I don't, if I study now, then I can't go watch a movie, but I want to get a good job. I want to go to college. I want to learn. I'm just interested in learning. So I'm going to study now, and maybe that takes away from something more immediate reward, but then I get some longer term payoff. So in reinforcement learning, if you're thinking long term and you want to maximize your overall, your sort of lifetime reward, or minimize your lifetime loss. And this ends up being quite different. You have to be a little clever about how you do this. And reinforcement learning, in some sense, is the broadest formulation of the machine learning problem, but it's not necessarily where the most interesting things are going on, because most of the interesting things are involving very complex, when the x's, the data points, are in some very high dimensional space, and they have some structure, and you want to recover that structure. So at least in my opinion, so a lot of the very interesting things going on right now are in these areas: these semi-supervised learning, active learning, unsupervised learning, the dimensionality reduction I mentioned earlier. These kinds of things are sort of where the action is.